So let's take a look at random utility models, which take away two key concerns about the individual and zonal travel cost model, namely competition and substitution between recreation sites, and as you start including multiple sites, we can also begin to look at the characteristics of a particular recreation site. So in order for this to work, we need to have observations, a number of individuals, here denoted I, who choose to visit a particular site G, but we need to have this for multiple sites, 1 to capital J. Now, the real preference, the fact that somebody chose to go to G, implies that to that individual, G is more valuable. Greater utility is derived from visiting G rather than J, so the utility for individual I going to G must be greater than the utility of individual I going to J, because otherwise she would not have gone there, right? So that is the condition that follows from this particular choice. Another key component in the random utility model is that tastes vary, so we decompose utility U into two parts. One, a deterministic part that depends on observables, and a second, a stochastic or random part that is idiosyncratic. And that is where the name random utility comes from. There is a fixed component or a deterministic component to utility and a random component to utility. So really the condition that we have is that the deterministic part plus the stochastic part is greater of site G is greater than the deterministic plus the stochastic part for site J, and that is true for all sites except the one that was picked. So that is a thing that we need to assume, and then we make the V, the deterministic part, a linear function or linearizable function of things that we think matter, such as income, travel costs, site quality, and so on and so forth. And here is one particular example where the deterministic part is income minus travel costs, so this is disposable income that remains. That this parameter is the same for the two of them is of course an assumption, and that's testable, plus the site quality that is here assumed to be measurable by one particular indicator, but of course you can use whatever you have data available for. So that is an assumption that we make, and then we assume that the error term, the random part of the utility, follows a Gumbel distribution that looks something like this. This is the standardized Gumbel distribution. And if we assume that Gumbel distribution, then this equation here, this condition here, that total utility deterministic plus random is greater than total utility for other sites, then implies that the probability of going to site G is the exponent of the deterministic part for site G over the sum of all alternatives of the deterministic utility for all deterministic part for all possible sites that you could have gone to. That follows from assuming that this epsilon here is a Gumbel distribution. If you were to make a different distributional assumption, then this closed form expression would not be possible. So that is a thing that we have here, the probability of going of individual I going to G. There's this thing here. We multiply this particular probability for all choices. We'll have a complete expression of our probability, right? It's not just that we choose G, but we also chose not H, right? So all those things go in there, and then we have an expression for the likelihood, and we do that not just for the choices of individual I, but also for the choices of individual K and individual L. And then we use maximum likelihood methods to we just obtain the entire likelihood. So now we're going to maximize that by choosing our parameters beta. And then we have essentially a demand function that depends on how the probability of visiting a particular site changes with changes in the site's quality. And of course, we can also then introduce a site that was prohibitively expensive, but reduce its cost, and in that way we add a site, or we can have a site that was prohibitively ugly and nobody wanted to go there, had a very low quality queue, and you can increase the quality and then people start going there, and vice versa. We can sort of play around with situations where a particular site becomes prohibitively expensive or prohibitively ugly and people don't want to go there anymore. We essentially remove a site from the choice set. Important thing to note is that with this particular model, we essentially model market share. So we model the probability of somebody going someplace conditional on them making a trip, but we do not model the choice of making the trip in the first place. So we need a separate model to calculate and estimate the number of trips. Another important thing to note about this particular specification is that we assume independence from irrelevant alternatives. So to give a local example, the relative probabilities of visiting Wakehurst or Sheffield, two gardens near Brighton, are independent whether or not the people who make the choice know about the existence of Standen, another major garden near Brighton. So you may like Wakehurst over Sheffield, and you will continue to like Wakehurst over Sheffield by the same proportion, regardless whether Standen is open or not, regardless of whether you know about Standen or not. So that is that follows from the distributional assumptions that you make again. And sometimes this is a assumption that can be justified, but sometimes it is not, right? But you always assume that in this particular model. That's the important thing to know. So how does this work, right? Let's look at a concrete example where from a paper published by Day and colleagues in 2002, and it's about KwaZulu-Natal, which is in South Africa. And they studied 4 different game parks. These are far away from where people live, so really you need to spend the night there, and that is where you actually where they actually charge you for. And also the reason that you need to spend the night is because most wildlife is most active at dawn and dusk rather than in the middle of the day. You could probably make a day trip there, but then you would be there when all the animals are hiding or asleep, right? So it really makes sense to spend the night there. And questions that you can ask with a study like this is how much welfare is derived from access to the park, how might this change with management options, how will revenues change in response to changes in pricing, and can the entry fees, can the accommodation costs, and so on and so forth. 4 parks were studied, the names are given here, I won't butcher them. This is an important thing to consider, right? So your choice sets is 4? Why not 5? Why not include the parks that are further afield around Johannesburg and so on and so forth? No, well, maybe it was data, maybe it is um, reasonable to assume that this is indeed the choice set, but this is an important study design issue. Those 4 parks are different in terms of quality. You would see different animals there, elephants, lions, and so on and so forth. And also the place where you would stay is different between the parks. They very purposely targeted the locals, and then of course it makes sense to say, well, these are the 4 parks that can be considered because they are within reasonable travel distance. So this is not about people flying in from London to see game in South Africa. No, this is about the locals enjoying this. Sorry. And then what they did was they had data for 26,000 bookings with all the details, where do you come from and so on and so forth, how much did you spend and how long did you stay, and then they sampled 1,000 of these bookings. Data on the address, where people lived, on the size of the party, accommodation type, visit duration, park visited, entry fee, accommodation fees, a lot of data. And then they use the geographic information system to work out 2 things. One, travel distance, and second, they started adding neighborhood socioeconomic data. So the form that people fill in when booking and when visiting did not disclose a lot of information, income or ethnicity. For that matter, it's always very important in South Africa. And for that, they actually used the neighborhood characteristics. So the assumption is that people in the neighborhood all have roughly the same income. That is sometimes a pretty tall assumption, but it's an assumption that they had to make. Travel costs were calculated from door to gate over the road, and then they had to make assumptions about the speed of travel and the fuel consumed. They had actual data on entrance fee and accommodation cost, but the cost of the cost of travel is essentially assumed from typical conditions. And then they also don't have the opportunity cost of time, but they do have the average weight of the place where people came from, and they stuck that into a regression as well and found that yes, it significantly explained things, but of course this is not as good as individual data. And then once they've made all these assumptions, and you can question a lot of these assumptions because some of them are peculiar and some of them are crude, but the important thing to note here is that you cannot avoid assumptions like these, right? You have to make these assumptions, and if you don't have proper data, you don't have accurate data, then you have to make it work somehow. And then here are some of the results that they found. So in this column here we have the per trip welfare loss if these parks would disappear, right? Or if they would be prohibitively expensive, or if all the animals in the park would be shot by poachers, so there is no reason to visit it anymore, right? The site quality has deteriorated quite considerably. So this is the consumer surplus per trip, and then this is if we scale it up to total visits. And the important thing here is, different sites have different values. So if you were, say, the minister responsible for this in KwaZulu-Natal, and you would have to choose, I have budget constraints, I have a fiscal crisis, I have to close one of these parks, which one would I preferably close? Well, the answer to that is Mkuzi, where you can see well, that actually generates the least welfare. So if we have to lose one, Mkuzi would be the proper choice. What you also see is nonlinearity in valuation. So they ran a scenario where Holloway would be closed and Umfolozi would be closed. And you see the welfare loss of these two. But they also ran the scenario where both of them would be closed. And obviously, 1 million is greater than 500,000 plus 300,000, right? So there is synergy in welfare. The welfare here is a nonlinear function of these. And of course, that is because you increasingly take away options. And if you close this particular park, then the other parks, because there is no substitute or there is less of a substitute for them, become more valuable, right? So you see nonlinearity in addition, exactly as it should. So this gives you some idea of the value of these parks to locals, and this is the use value. So this is not the total value because it excludes non-use values, it excludes existence values, and it is only the value to the people who live nearby rather than to all people. But it gives you an idea of what these methods can do.